Okay. Okay, so our first speaker today is Liliana Rivera Sandoval from the University of Alberta, who will talk us about the outburst in, this AM cataclysmic peculiarities and importance of in the survey era. So please, Liliana, can you share your screen?
Yes.
And yes.
So it's visible there, right?
Yes, that's perfect.
Okay. Do you hear me well there? Do you see my cursor as well?
Yes.
Yeah. Okay. Well, hello everyone. Thank you very much to the organizers for giving me the opportunity to share with you all some results regarding the outbursts in ultra-compact white dwarf binaries, also known as AM CVn systems. So I would like to start. I would like to start the talk by making a comparison between different kinds of accreting white dwarfs. So on one hand, we have the cataclysmic variables, in which we have a white dwarf accreting from a low mass star, let's say a star like the sun. We know they are hydrogen abundant and they have periods of a few hours. We know thousands of those systems. On the other hand, we have the AM CVn systems, in which a white dwarf is accreting mass from another white dwarf or from a helium-rich star. So contrary to cataclysmic variables, these AM CVns have no hydrogen. Instead, they are helium abundant. And one thing that is very interesting about these binaries is that they have very short orbital periods. They can have orbital periods as short as 5 minutes, which is just mind-blowing. And we know few of those systems, approximately 60 of them, all in the solar neighborhood. And this is very interesting because it contrasts a lot with models. There are some models that actually predict that even within 1 kiloparsec, we should observe 1,000 of those systems, and it's not what we are observing. So this raises the question whether we are overestimating, let's say, the deformation of these binaries, or whether there are some heavy observational biases that we have to overcome. And in order to possibly answer that question, we need to further understand a little bit more the evolution of these binaries. We know from modeling, for example, that AM CVns can be the result of 3 different evolutionary channels. All of them, let's say, will reach their minimum orbital period here, depending on the channel. And we know that as these binaries evolved, they will decrease the mass transfer rate from the donor, and the binary will widen, and they will become fainter. And this will happen as the binary evolves. So actually, most of the AM CVns are expected to reside on the long end, let's say, of the orbital period distribution. And these binaries, as they become older, of course, they become fainter. So it's difficult many times to observe them when they are in quiescence, because they are many times below the detection limit of some smallest telescopes or all-sky surveys, let's say. So many of those binaries actually that we know have been detected when they are in outburst. And this is because they become several magnitudes brighter in that state. Now, I'm going to talk about outburst, and therefore I would like to describe a little bit the paradigm that we know for these binaries. We know that we can separate these systems into persistent and transient sources. So the persistent systems may or may not have an accretion disk, depending on the orbital period. So for systems with orbital periods of less than 10 minutes, there is no space actually to form an accretion disk, and therefore the mass transfer happens through an accretion stream. At a slightly longer orbital periods, the binary is a bit wider, let's say, and then we have an accretion disk there. But this disk is hot and is stable because the mass transfer rate from the donor is, let's say, sufficiently high to keep it in that state. But something happens at around 20 minutes. And so the model that we usually invoke to explain the accretion in AM CVn systems is the disk instability model. So under that model, the mass transfer rate from the donor is constant. And the value of that mass transfer rate is the one that defines the stability of the accretion disk. So for systems at orbital periods, let's say longer than 20 minutes, we start observing these unstable accretion disks, and therefore we see outbursts. The frequency of the outbursts decreases as we move towards longer periods. And this instability model actually predicts that for long period AM CVns, the mass transfer rate from the donor is so low such that actually the accretion disk there is cold and is stable. So we shouldn't see, let's say, outbursts in those systems. Where is, let's say, the boundary between unstable and stable disk is not clear, is something we are trying to understand from the observational point of view. Because for models, for example, this limit changes based on the mass of the accretor, the composition of the accretion disk, and other parameters. So, but by exploiting the power of light curves, we can get some insights about the physics in these ultra-compact systems. So the first of the studies, let's say, that try to characterize the outbursts in AM CVns and how they are related to the orbital period was the one by Leviton et al. So they took data from different missions, from different surveys, and study the long-term light curves of AM CVns. Here I am putting an example of those light curves. So these authors, what did was like to derive the relation between the orbital period and the recurrence time of these outbursts, the amplitude of the outbursts, and the duration of these outbursts. As you see here, here are the relations respectively with the orbital period. Now, one thing that we have to consider here is that this model, let's say these empirical observations or these empirical relations were derived for systems with orbital periods up to around 37 minutes. And this is because, as I mentioned before, the recurrence times in systems with long orbital periods, they take a lot of time, several years. And so it's sometimes, let's say, difficult to get observations for those systems. But at shorter orbital periods, we see that these systems go into outbursts more often, and then it's kind of easier to characterize them. So then everything, let's say, beyond this orbital period is just an extrapolation of this relation. And here it comes, the importance of one of the first systems I wanted to discuss in this talk. And this is SDSS 1411. This is an AM CVn that went into outburst for the first time in 2018. It has an orbital period of around 46 minutes. This object was shown, let's say it's shown the amplitude of the outbursts very, very large, like 7 magnitudes. Until very recently, it was the AM CVn with the largest amplitude observed so far. And we obtained observations in different bands for this system, in X-rays, in ultraviolet, and in optical. And we saw some interesting characteristics. First, we see that there was a correlation between the ultraviolet and the optical. So when the binary was reaching the peaks, so both bands were reaching, let's say, the maximum values. But the same didn't happen with the X-rays. There was actually an anti-correlation with the X-rays here. This behavior has been observed in other accreting white dwarfs, for example, in SS Cygni, and might be related, for example, to the boundary layer becoming optically thick and then preventing the observation of these X-rays, and later becoming optically thin, and then is when we start observing more X-rays. But that is something that we have to further study. So we need to get more observations in X-rays and ultraviolet of AM CVns during outbursts, because those bands give us information of the inner parts of these binaries in that state. But not only that. So when we plot the duration of this binary, let's say in the orbital period and duration of outbursts, together with other systems, let's say on the long end of the period distribution, we, let's say, get this relation that is much flatter than the empirical observation, the empirical relations derived before, the one I mentioned before from Leviton et al. So this shows the importance of having, let's say, of sampling a longer parameter space. So with this system, we kind of updated this relation. And up to here, everything was, let's say, coming together nicer. So this instability model was telling us about how the accretion happened in these binaries. But later, so there were these other two systems with longer orbital periods that actually show a lot of interesting characteristics. So these binaries, SDSS 0807 and SDSS 1137, with orbital periods of 53 and 60 minutes respectively, show these outbursts that lasted longer than a year. And this is very interesting because these durations have not been observed in any other AM CVn or even in cataclysmic variables. So not only that, but also the amplitude of these events was low compared to what is expected from the disinstability model or from the empirical relations. So in this case of SDSS 0807, there were still, let's say, some arguments to explain these low amplitude, which are related to some inclination effects, for example. But the same argument doesn't apply with SDSS 1137. So this suggests that actually this might be something intrinsic to the mechanism that triggers these outbursts in long period systems. Now, in the case of SDSS 0807, I would like also to discuss a little bit about the X-ray observations during the post-outburst cooling phase. So we were able to obtain X-rays and ultraviolet observations during that stage, and we detected actually X-rays, and 1 month later, we didn't detect these X-rays. So these X-rays are actually coming from ongoing accretion during this post-outburst cooling phase. And this is because while the white dwarf gets hotter during the active accretion period here, it never reaches the temperatures to emit X-rays by itself. So these X-rays actually are coming then from accretion ongoing in that binary. And this accretion actually changes fast because 1 month later, we didn't detect it anymore. It's unclear here whether the non-detection is due to, for example, the binary stop accreting or whether it was just below the detection limit of our observations. But in any case, the duration of these two systems, when we plot it again into the orbital period and outward duration relation, we see here that these two binaries are far from expectations, let's say from the disinstability model by several times, no? And this is telling us that there is some other mechanism that is not instabilities in the accretion disk that are triggering these outbursts. This mechanism seems to be enhanced mass transfer from the donor. What is the mechanism that is, let's say, making the donors to send more mass is unclear. Could be irradiation of the donor, for example, or some magnetic cycles, even some pulsations. That is something we have to further study in these systems. And so the fact that these outbursts don't come, let's say, from this instability gets supported when we get actually some studies on the evolution of the colors of these systems. I am putting here first as comparison SDSS 1411, the first system that I mentioned before, and a cataclysmic variable of the type dwarf nova and how the color evolution happens in those systems. So we see that in the case of SDSS 1411, this binary, as it reaches the peak, becomes bluer, becomes hotter, and it becomes brighter, as, let's say, is expected for cataclysmic variables under this instability model. So up to here, we are fine. The duration of these outbursts as well, you remember, agrees with the traditional model. But the same doesn't happen when we do the same exercise for the long period systems. In fact, these systems, when are close to the peak, these binaries actually become brighter, but they become redder. So the colors actually indicate that these systems never reach the temperatures to ionize helium, which is the, let's say, the reason of why there are instabilities in the accretion disk. And so then this strengthens the fact that these outbursts in long period systems are apparently not coming from the disk instability model, and instead they are having other mechanisms like the enhanced mass transfer. And this is important for several reasons. One thing I would like to mention here is that AM CVns, because of their very short orbits, are expected to be detected by LISA as background, but also as resolved sources. So what happens if actually the enhanced mass transfer from the donor is making these binaries evolve faster towards longer orbital periods, because the donor is losing, let's say, mass much faster than we actually believe. So this, of course, will change the period distribution that we actually believe. And this will, of course, change as well some of the predictions on the number of systems that we are expected to detect with LISA. So that is something that we need to model, to include in the long-term evolution of these systems in order to assess what the impact on, for example, a gravitational wave astronomy these systems may have. But we are not only studying the long-term evolution, let's say long period system, but also the short period systems. So in this case, we are also performing survey of AM CVns with TESS. TESS is this planetary mission that observes a specific part of the sky for 1 month and continuously. So you get exquisite light curves of a specific system. In this case, we are using it to study the outbursts in AM CVns. And as you can see here, you get exquisite light curves in which you see a lot of details. So you see the precursors, for example, the super outburst, the full super outburst. Sometimes it's difficult to see all these events from the ground. So this telescope is allowing us to see all these details. We see as well these echo outbursts. So we are getting a lot, let's say, of the characterization of these systems. We are getting better constraints for models. And in fact, when we compare, let's say, the curves that we are getting with these instability model systems, but models that have as well enhanced mass transfer, we see that these, let's say, models better reproduce the observations. So this is telling us that enhanced mass transfer might be present as well in short period systems. And again, this is another reason of why we have to include those mechanisms into the evolution of these binaries. This work is being performed by my PhD student, Manuel Pichardo Marcano at Texas Tech University, and we expect to publish it very soon, so please stay tuned. And I would like just to finish here by stressing that we need multi-wavelength studies of AM CVn during outbursts. We saw that X-rays and ultraviolet are needed in order to understand the inner parts of these systems. With the study of long period AM CVns, we have unambiguously proved that there is this enhanced mass transfer mechanism that is triggering outbursts in those systems. This is something interesting because it was thought to exist in AM CVns, but was never, let's say, proved before. And so now we have the observations. We now need to understand what is triggering this enhanced mass transfer. Could be irradiation of the donor, for example, some magnetic cycles or even some pulsations there. So we need to understand there, to do more modeling on how this mechanism can impact not only, let's say, how to understand how the accretion happens in these binaries, but also how this can impact the long-term evolution of AM CVns, and how that can, of course, have an impact on LISA's background detection and the number of resolved sources that we are expecting to detect. So we are as well having these exquisite light curves at shorter, for systems that are in the shorter end of the period distribution. And we are getting a lot more physics there, understanding what is going on in these binaries. And that is something that we are trying to understand. So I'm going to finish here, and I will be very happy to take any questions that you may have. Thank you.
Okay, thank you very much for the presentation. It was very interesting. So, questions? Do we have? Does somebody have a question? I'm not. There are two hands raised here. There's in the chat. Okay.
Marcelo, there
So
is one in the chat.
yes, that was what I was going to read right now. Yes. So Sandro Merenghetti asks, the shape of the outburst light curves in 08, 07, and 1137 were rather different. Can we learn something from that?
From these two?
Yes.
Yeah, well, the shapes are different. Well, so one thing here is that we have not coverage on this part, for example. No, what we, let's say this data in this specific case comes from CTF, and based on the CTF data, what we just determine is, let's say, we get an estimation on the duration based on the, let's say, XMN data we had together with the CTF. But there is here a part that we are missing. And maybe the shape is in general terms, let's say, similar, but we have no coverage there. But we have these characteristics that are similar in both cases, which is long-term duration outbursts and low amplitudes. So that is something that seems to be characteristic of these objects.
So we have a couple of questions more. So then there is a question about the theoretic gravitational wave characteristics from these AM CVns. I don't understand what this starring thing is. Can someone tell that to me? But it's how much would be the theoretic gravitational wave characteristics? Starring? I don't know what
strain.
Is strain. Oh, okay, thanks. From the AM CVns.
Yeah, well, it will depend on the mass of the components and the period of those systems. Some of these binaries are actually AM CVns, a few of those systems. So you can see here, for example, they have characteristic strain of 10 to the minus 19, no? And some of those systems, let's say the ones that have longer orbital periods, are being part of the background, gravitational wave background here, which are in the range of 10 to the minus 20, 10 to the minus 21, for example. Yeah, so.
And then we have another question where we have time for a couple of more questions, so I will read some of them, and then the rest of you can join for the talks afterwards, for the discussion in the breakout rooms, I guess. So Tom Marsh asks if we understand why the enhanced mass transfer makes the systems redder.
I don't think we fully understand that. That is, it's just, I think the colors becomes, I will go there here actually. So the accretion disk, of course, gets hotter. So because there is this mass, let's say, going through the accretion disk. So that's why it becomes brighter. And that's why actually, let's say, I think it becomes redder. The exact details on the model, I cannot give them to you because actually there has not been a lot of modeling for AM CVns. No, we know there are several models for cataclysmic variables, but there are like few models, detailed modeling for AM CVns, and that is something that I want to stress here, that we need as well more modeling for these systems. Now that we have observations that are telling us about additional mechanisms, we need to model these binaries in order to understand timescales, colors, etc.
Okay. I think we will move to our next speaker, and as I said, I encourage the remaining people that wanted to ask questions to meet Liliana in the breakout rooms after the next talk and ask her. I think it will be very fruitful, so I encourage you to do it.